Okay, option E2, stellar radiation. Stellar radiation is an extremely important topic because everything that we know about stars comes from the light or the radiation that we receive from them. And stars are essentially a giant ball of gas which has a nuclear reaction at its core. Stars become stars when that nuclear reaction ignites. And when that nuclear reaction ignites, then the inward pull of gravity is going to stop, and the outward push from the pressure of the heat at the core is going to cause the star to reach some point of balance or some point of equilibrium. So the pressure that results from the heat of the nuclear reaction pushes outward, and then that's balanced by the inward pull of gravity, or just much more simply, the gravity balances or is equal to the radiation pressure out. And when that occurs, the star is now stable and will now exist like that for millions or even billions of years in that same state. Now, because ultimately the main power source for stars is nuclear fusion, we do need to examine the equations, and it turns out that there's a couple of different ways in which the fusion process can actually work for stars. Most stars are converting hydrogen, the simplest element in the universe, into helium, the second simplest element in the universe. Now, there's a couple of different ways that they can do it. I'm going to show you one path, and most importantly, I'm going to kind of summarize all of the equations into one equation. That last equation that I give you, that's really the most important one. So the nuclear fusion process begins when we combine one hydrogen with one hydrogen, and this produces a form of hydrogen known as deuterium, and then it also produces a couple of other particles. So we also get a positron, this is the positive particle, and we get a electron neutrino. Okay, so the important product is this portion right here. We've produced deuterium. Okay, now you might notice that I had hydrogen on the left. I also have hydrogen on the right. It's still hydrogen. What happened to the other hydrogen? The other hydrogen was turned into a neutron. The other hydrogen was turned into a neutron. So now, in this new form, I have a mass of 2 because I have one proton and one neutron. Now this deuterium will undergo a reaction itself. And what I will essentially do is add that to another hydrogen. Another hydrogen fuses in. This is the third particle to come in. And now, when this hydrogen particle is added, or this proton, in essence, is added, it won't undergo a change. It will actually remain as a proton, and I now have a mass of 3, but a proton number of 2. And in this case, I also release a gamma ray. I realize it's a little confusing. These symbols look fairly similar, but the neutrino is the little squiggly V, and then the Y, the weird shaped Y, this is the gamma ray. So in this case, I produce a helium nuclei, but only has a mass of 3. The typical helium nuclei has a mass of 4. So now at this point, a kind of an unusual thing is going to happen. I'm going to bring 2 of these particles together. So I'm going to have 3,2 helium, and from some other reaction that's undergone this same process, I'm going to add another one of these guys to produce the final product, which is the normal helium nucleus, helium 4. But I also, if you notice the masses, the mass numbers don't work out. Here I have 2 and 2 is 4, and here I have 2, so I'm missing 2. Up here I have 3 and 3 is 6, over here I have 4, I'm missing 2. Where do those particles go out? They go out as 2 hydrogen. Okay? So, in the end, what's the end result of this? Well, the end result of this is this. This is the final equation that you really should understand. I'm going to add 4 hydrogen together. And on the right side, I'm going to produce a number of particles. Now, here's the important thing to understand. In going through these first steps, I have to go through them again to produce this second helium-3. Right? So I went through these 2 steps, I produced a helium-3. That accounts for this guy. But this guy, he must have been accounted by another set of hydrogens somewhere else in the star, also undergoing the same process to produce this guy, to produce this. So that means that I'm going to get 2 of these guys, 2 of these guys, and 2 of these guys. Okay? And the reason is because I'm going through both sets of equations twice to get each of the 2 helium nuclei. So as a result of that, I get my helium, but I also get 2 of my positrons, I get 2 electron neutrinos, 0, 0, and I get 2, 0, 0 gamma rays. This is ultimately what powers the star. Now back here, each one of these was releasing energy. What was the form of the energy? Well, mostly the form of the energy was kinetic energy, with the exception of the gamma ray. This was one of the forms of energy. It turns out that the reaction that creates the most energy is actually this last step. Right? In this last step, where is the energy where is it going? It's going into the kinetic energy of these 3 particles, the helium nuclei and the 2 hydrogen particles. So this is what ultimately powers the stars.